NMR information, you would be hard-pressed to know what's going on. Basically, let's look at the porosity track. So this is porosity from 0 to 30 pu. The blue dashed line is the conventional display for neutron porosity, and it's got its ups and downs, and there's a low point here, but it's basically kind of reading very high. It's reading sort of about 25 pu. Meantime, the density porosity, which is red line, is very low here at the top, then sort of jumps up, and then goes down low again. Now, the classic signature for gas in classic well log analysis is the neutron and density logs crossing over. So if neutron goes low, neutron is sensitive to hydrogen index, which for gas is low. So in a gas zone, neutron will go low. Density actually will go up a little bit. Density, that's the way sort of the density equations work. The density porosity goes higher. So you'll have a crossover of neutron and density, which in the water zone are together, and then in the gas zone, density goes up a little, neutron goes down a lot, and that's your classic gas indication, density-neutron crossover. Here, neutron is always higher than density. Now, the density is going up here, and the sharp log analyst notes that gamma ray has a drop-off at the same point, indicating moving from a shaly section into a cleaner section, but still it's quite ambiguous. I mean, up here, what's surely going on is that this is a shaly section with a lot of clay. Neutron tends to read high in clay, so that's kind of expected. Density porosity is usually a pretty good porosity measurement in clay. But although the density comes up, the neutron does not drop down, and they never cross over. So what is going on? The problem is resolved when you run the NMR tool, which is coded in solid black. And there, we see that in the shale zone, NMR and density agree exactly, and that's often the case. And that's a very, very handy thing. However, in this zone, which is the sort of the questionable zone, we see NMR quite a bit lower than density. So because NMR has a lower hydrogen index in gas than water, we say, aha, I bet there's gas there. And then you use those equations to solve for the porosity of the formation and the gas saturation, which would be really hard without the NMR tool. I mean, maybe impossible. And then here we can go back in the machine. So this is sort of an example where, again, NMR is kind of uniquely valuable. I will say, just looking at the T2 track, again, in the shaly zones, we have T2 very short because in clays, T2 reads very low. You might remember from part 1 of the series. Down here, in this shale, again, T2 low. Here, it looks like we have a pretty good, fairly clean sand without much clay. And the neutron is high because the porosity is actually higher, even though there's no clay. But here, the neutron is just, can't tell the difference between low porosity and lots of clay and no clay and high porosity. So it's not really very helpful. But NMR really does reveal what's happening. So this is, by the way, not unusual. Very typical. Another example of how the no hydrocarbon signal is so useful. This is gas hydrate, which is a very, very peculiar form of hydrocarbon. It's basically methane frozen into ice. It exists in vast quantities immediately below the sea floor at all latitudes and in the Arctic. And potentially a large source of natural gas someday when we run out of gas, but certainly of considerable interest to countries like Japan that have no other, this is the only game in their town, so the Japanese have been at the forefront of this. But working with the Japanese, we logged gas hydrate well, and density porosity is pretty healthy throughout the section here. The porosity scale runs from 0 to 0.5. And you'll notice the porosity is always plotted backwards. That's Schlumberger for you, but it's always the way it's done. 0 here, 0.5 here. Not much happening in the density porosity. We do have what looks like a high porosity streak, which is actually a coal. So there's no porosity here, but the density of coal is low, so it looks like a high porosity rock. If you're assuming it's a sandstone or limestone, but it's actually just pure coal. Okay, so now we run the NMR, and down here, CMR and neutron porosity agree exactly, as they very frequently do. CMR is not particularly fooled by coal, it doesn't care. But up here, there's a huge deficit. Okay, what's going on? There's certainly no gas. Gas does not exist in this formation. But this is where the gas hydrate is. Now, I told you that gas hydrate is natural gas, methane, frozen into ice. Now, if you think of things that have lots and lots of protons, the two top things on your list could be methane and ice, because they both are loaded with protons. But gas hydrate is a solid, and both the water is frozen into a crystal, so its NMR relaxation time is so short, it's not sensitive, the tool is not sensitive to it. And similar experiments like this that I've done showed that methane is also frozen, very important. So methane is not freely rotating in its little ice cage, it's actually frozen. And so it has no NMR signal either. Again, for the same reason that protons in solids relax way, way, way faster than the tool can sense. So, hence, no tool signal. And from the difference between the density porosity, which is real porosity, except for coal, and NMR porosity, which is just representing the water that's in the formation, the difference is the volume of hydrate in the formation that's added to the water. And you can get a precise assay of hydrate, and in fact, that is the way that gas hydrate is assayed all over the world. So again, no signal can be good. Yet another example of zero or no NMR signal being a good thing. This is bitumen, which is very heavy oil. Basically, it's behaving like kerogen. And again, let's just sort of look at the logs here. This again is a really interesting example. Gamma ray very low, no clay, all clean sand. That's good. Resistivity high. This is from 0.2 to 2,000 ohm meters. The entire formation is. This is from 2 to 2,000. The entire formation is above 40 ohm meters, and some goes up to hundreds, which anybody would say, wow, fantastic hydrocarbon zone everywhere. But not really. I mean, there is a lot of hydrocarbon, but you'll notice, and the water saturation from resistivity is shown in this blue or black curve over here. You can see it's fairly uniform, low water saturation. This is running from 0 to 1 in this entire well. But if you do the NMR assay, you get a zone here of very high water saturation. And the reason is that although you have high resistivity, the water, this is a very shallow formation, the water is so fresh that it's basically sort of looking like oil. So the NMR is able to now what's happening here is that the NMR signal is high here, it's near density and porosity, so that's good. Everywhere else, it's very much lower. So up here, it's very low because it's not seeing the hydrocarbon, which is bitumen. The porosity is much lower than the neutron in density, so we have tons and tons of bitumen here. Up here, we have no bitumen. There's no light oil here, so this must be water. So the NMR water saturation is high, and indeed, comparing to the core measurements, which are green, would show that indeed this is a water zone, a little bit of bitumen. And the reason is that the water is a very, very high resistivity, which is fooling the resistivity tool. So there's a number of fascinating things going on. We estimate the bitumen volume from the difference between the neutron density porosity here, which is high throughout the entire formation, but NMR is incredibly low because we're not seeing this very, very heavy oil, which has relaxation time way too short to be seen by the tool. Yeah.
So again, in both of these examples, this slide and this slide, you would have neutron hydrogen index, which would pick up this more than the hydrogen atom, and that will coincide with the MR, those signals. That would be very big.
Okay, I should make it clear that the neutron hydrogen index and the NMR hydrogen index are not the same. In fact, it's unfortunate they have the same name. Neutron really does see all protons, and it is indiscriminate. It'll see protons that are in solids, such as in gas hydrate. It'll see protons in water's hydration, like in gypsum. NMR doesn't see those because, although the protons are there, they're relaxing much too short for the NMR to see. Neutron doesn't have a good time issue. Similarly, with this bitumen, which is very, very heavy oil, like Keragen, it is loaded with protons. Neutron has no problem seeing it. But because the viscosity is so high, millions of centipoise, it's way too short to be seen by NMR. So the NMR has the big porosity deficit here relative to neutron, which is agreeing here with density information. So that's why, so when you see NMR going much lower than neutron, then you know hydrogen index is not the same. Two different hydrogen indexes.
So that means that here neutron has two branches. What you see is neutron density here. N5, this N5 is sort of neutron porosity, but it's not neutron index, hydrogen index.
I'm not quite sure I'm understanding your question.
Is the neutron being interpreted with a low hydrogen index?
No.
Because the bitumen ought to be deficient in hydrogen relative.
It's a little bit. Yeah, the neutron hydrogen index of bitumen is going to be in the range of 0.9. It's not. And so I'm not going to swear about the 10% effect on the hydrocarbon signal here, but heavy oils are somewhat deficient in hydrogen, and it depends, of course, exactly what the viscosity of this stuff is, but generally not hugely deficient. The neutron does not usually read very low.
Well, you showed a chart earlier that had a hydrogen index as low as 0.7.
That's NMR hydrogen index. That's NMR signal versus viscosity. Yeah, so that's NMR. Neutron sees all protons. That also answer your question?
So it's up here, the neutron just from CNT2. It's not from the neutron, the tiny hydrogen, the pick up a hydrogen index, not the neutron velocity.
Okay, maybe we could talk about this later. I think this is now perhaps a bit more technical. Yeah, we can discuss that.
But I don't know if it's an issue, but in your solution to the linear equation, density, porosity, NMR porosity, you had to assume the hydrogen index of hydrocarbon. There was only one hydrogen index,
Yeah.
hydrocarbon. So does that limit the applicability of this technique to single hydrocarbon phase reactions? I mean, like you have either hydrate or gas or bitumen, but never a mix.
Okay, so if you remember my discussion about ELAN in part 1, and you were here for part 1.
Yeah.
ELAN, you could put as many terms into it as you want. So you can have, when you have in the composition vector, if you will, you can have light oil, heavy oil, gas, Keragen, and each one of those has different NMR parameters, different neutron parameters, different density parameters, and then you do the matrix inversion.
So this
now,
is a simplification.
this is a vast simplification, but this is so simple that you could just read it off the log, with the NMR reading very low neutron density and agreement. You don't really need an ELAN analysis here. It also is a very clean sand, so this is a really uncomplicated situation. The main complication is that the water is so fresh. Okay, so we are just about at the end. Now I've got, this is the part of the talk which when I have presented it to clients, they actually like the best, and I usually do not have this phrase when I present to clients. That's taken out. And I think this is more of a sort of general sort of Schlumberger and client relation sort of thing than anything specific you're going to learn. I'm not going to go through these troubleshooting tables. I'm just putting them up. I'm going to just whiz by here. Just to show you that it is very, very useful to write down in an organized way everything that can go wrong, and systematically say, okay, why can it go wrong? And with a client, I will go through these slides very slowly and carefully. And that is something that is really, really appreciated. So let's see if I can find one interesting one. So yeah, this is a common one. Okay, so what if you have TCMR reading way high, but with T2 of 20 milliseconds? Well, that is almost certainly a washout, and that means you should ignore NMR data at that depth. And if you think you're going to have a lot of washouts in your well, you shouldn't use this tool. It's important to have an alternative. Sometimes I've recommended that the competitor, they'd be better off with a competitor tool. Better to be happy with a competitor than unhappy with us. You don't want to be unhappy with us. So again, I think from a sort of client relations standpoint, if you can point out what can go wrong, that makes you a trusted expert in your data logging technique. And coming from research, that's really one of our main roles, to be trusted experts in the industry.
Why
So,
is T2 short in that case? Or relatively short?
yeah, because whole mud relaxes fast because it's so full of clay. It's got so much clay in it. Mud that's invaded into the formation relaxes slower because the clay is left behind the mud cake. Go through all these teachings. But anyway, if you can tell the client where to interpret with caution, where to use special inversion software and so on, that's really appreciated. So that's something you should keep in mind when you're presenting yourself as an expert in your technique, which is what we all should be. So with that, I will just conclude. I also showed this last time, but these tools can be a lot of fun. So here's the CMR about to be dumped into Monterey Bay on a unmanned submarine. It's been to the North Slope of Alaska. It's been to Colorado, and of course, there's the Sunrise Sea. So anyway, thank you again for your attention. If you have any more questions, you can come and see me anytime. Excuse me. Slides will be made available. No video, I guess. But anyway, thanks a lot.